Hello friends, here in this video we are going to see the reversible adiabatic process, also called as isentropic process, in detail. Let us get started. So the reversible adiabatic process, also called as isentropic process, it is that in which the amount of heat transfer is zero. It means no heat is transferred into the system or no heat is transferred out of the system. So we can imagine a reversible adiabatic process or an isentropic process in such a way that it is a completely insulated system. That I can show it with the help of a diagram. Now, here I am taking a cylinder inside which there is a piston and gases are contained below the piston. If it is adiabatic process, it means this cylinder is completely insulated. So here this indicates that it is an insulation, and because of this insulation the amount of heat transfer is equal to zero. So adiabatic process can be imagined, or the reversible adiabatic process, in such a way that it is an insulated cylinder from which neither the heat can transfer out nor any heat can come inside this system. So it is a reversible adiabatic process. At first, for the reversible adiabatic process, I am going to derive a certain relation between pressure and volume. Let us get started with this first. So I'll say that the first heading is relation between pressure and volume. For this, I'll use some basics, that since small amount of heat transfer is equal to small amount of work done plus small amount of change in internal energy. So here I am writing the relation that therefore small amount of heat transfer I'll denote it as dq, small amount of work done dw, plus small amount of internal energy, or the change in internal energy, that is du. Next, keeping this as equation number 1, now I can say that also the change in heat transfer is zero because it is the isentropic process or the reversible adiabatic process in which there is no heat transfer either from the system or to the system. Next, I can say that also the work transfer dW is given by P into dV, that is pressure into small change in volume, because area under the PV diagram gives us the amount of work done. So finally I can write equation 1 in this form, that is therefore here I have written dW plus du. I'll shift du here, so du plus dW, so that the answer comes in a specific form. So it will be du plus it is dW which is the small amount of work transfer. For TW, in place of it I can write P into dV, and that is equal to dQ, which is the amount of heat transfer, and that is 0. So it is equal to 0. Next, I will be keeping this as equation number 2nd. Then after reaching here, I can say that since PV is equal to mRT and it is the characteristic gas equation, so therefore if I bring mass here, so volume upon mass is called as specific volume, and that is equal to RT. I'll write down, since volume divided by mass, that is specific volume. Next, therefore instead of P I can write it as RT divided by this small volume. Next, I am going to shift this value in equation number 2nd, that is replacing P with RT by V. So therefore put the value of P in equation 2nd. So we have delta U or du will remain as it is, plus instead of P it is RT upon small v into dV, and that is equal to 0. Next, after reaching at this stage, I can say that change in internal energy du, since the change in internal energy is given by mCV T2 minus T1. So therefore if I assume mass as 1 kg, so it will be CV, and temperature change T2 minus T1 can be written as dt. So I'll replace du with CV dt. So du will be replaced. Here I have CV dt plus RT upon small v into dV, that is equal to 0. I have used this relation assuming mass is equal to 1 kg for gas. Next, after reaching at this stage, I will be dividing throughout by capital T, which is the temperature. So therefore dividing throughout by capital T. So I will have the relation CV dt upon, here I am having CV dt, so that will be dt divided by T plus RT upon V it is, so dividing by T into dV is equal to 0. Here we are dividing by T and 0 divided by T, that the answer is 0, so it will remain as it is. Next, after reaching here, therefore CV upon into dt by T will remain as it is. Here T and T will get cancelled out. So we have plus R into dV upon V is equal to 0. Next, therefore after reaching at this stage, I'll say that integrating we get, now when I am integrating this, CV will remain as it is, integration of dt by T plus R is a constant, that will also remain here, integration of dV by V is equal to integration of 0, then CV integration of 1 upon T with respect to dt, that will give us log to the base e, which is written as ln. So ln T plus R into integration of 1 upon V is log to the base e, which is ln V, and integration of 0, that is a constant. Now we have reached up till this stage in the derivation. Instead of T, I will write it in this way, that since we know that PV, that is pressure into volume, is equal to RT, So therefore T is equal to PV divided by R. I'll use this relation here, replacing T with PV upon R. So I'll get it in this way. Therefore CV ln of PV divided by R plus R ln V is equal to 0. Next, after reaching here, dividing throughout by CV, which is specific heat at constant volume. So therefore CV upon CV ln of PV upon R plus R upon CV ln of V is equal to, now here it was a constant, not 0 because we have integrated, so this is a constant. Next, therefore CV upon CV will get cancelled out, 1 remains here. So we have ln of PV upon R plus R upon CV ln of V is equal to C. Next, I'll explain another relation here, that since Cp upon Cv is called as gamma, which is adiabatic index, this gamma is called as adiabatic index, and therefore Cp will be equal to gamma into Cv. Next, also Cp minus Cv is equal to R, which is called as characteristic gas constant. So instead of Cp, I'll write down gamma Cv minus Cv is equal to R. Cv I can take common, so here I have gamma minus 1 is equal to R. So therefore R upon Cv, I'll send it onto the other side, is equal to gamma minus 1. This is one relation which I am getting here. And next I am also getting Cv here. Cv will be equal to R upon gamma minus 1. So next, after reaching here, I'll write it down in this way, that ln of PV upon R plus, now R upon CV can be simply replaced by gamma minus 1. So gamma minus 1 ln of V is equal to C. Then since as per the rule of ln, here there is plus sign, so it can be written in the form of multiplication. That is, therefore I'll get it in this way, that ln of PV into, now this term first I'll simplify before multiplying. It can be written as plus this ln gamma minus 1 can be written as raised to the power, this is one and the same thing. If I write it, it would be gamma minus 1 into ln of V raised to gamma minus 1. Now I can multiply them, so that will become ln PV into V raised to gamma minus 1 and dividing this by R, and that is equal to a constant C. Next, on simplification, here the raised to power is 1, so this will be V raised to 1 plus gamma minus 1, so plus 1 minus 1 will get cancelled. So the complete answer of this term is P V raised to gamma divided by R is equal to C. Next, if I take anti-ln, it means if I shift this ln onto the other side or taking anti-ln on both the sides, so this anti-ln and ln will get cancelled. So here I would be having PV raised to gamma, and this will be anti-ln of this entire constant will give me another constant. I'll say that it is constant here, another constant, and then if I have R here, multiplying it with constant, that will give me another value, so this entire term is constant. So I am getting PV raised to gamma is equal to a constant, and for state 1 and 2 it can be written as P1 V1 raised to gamma is equal to P2 V2 raised to gamma, which is equal to constant, and this is the law governing reversible adiabatic process. So it means whenever there is a reversible adiabatic process from state 1 to 2, we can use this relation P1 V1 raised to gamma is equal to P2 V2 raised to gamma, which is equal to constant. Now after getting the relation between pressure and volume, now I derive another relation, that is between pressure, volume and temperature. Let us get started. So it is relation between pressure, volume and temperature, and this is for adiabatic process. Now I'll start it in this way, that since the characteristic gas equation is given by PV is equal to mRT, so therefore P V, if I shift m here, so it will be V upon m. Now V upon m is called as volume upon mass, which is specific volume, so that is equal to RT. Next, from this relation I'll get P is equal to RT upon V. I'll be keeping this as my first equation, and here in this equation I'll say that where capital R is called as characteristic gas constant. Its unit can be in terms of kilojoule per kg Kelvin, or it can be in terms of joule per kg Kelvin. So that is R, the characteristic gas constant. Now I have got pressure is equal to RT upon specific volume, that is V. Next I'll also get from here, therefore V specific volume will be equal to RT upon P, and this I'll keep it as second equation. So from the first relation I have got pressure and specific volume. Pressure is in terms of temperature and specific volume. Similarly, specific volume is in terms of temperature and pressure. That is equation 1 and 2. Now I'll use the governing equation which we have derived before. That governing equation was PV raised to gamma is equal to constant. I can write it for a general state. So therefore I'll say that since PV raised to gamma is equal to constant, now therefore here I'll put the value of P from equation number 1, which is RT upon specific volume. So RT upon specific volume into specific volume raised to gamma is equal to constant. Next, after reaching at this stage, therefore RT I'll keep it as it is, V raised to gamma, which is specific volume. This V is raised to power 1. If I shift into the numerator, that becomes raised to power minus 1 is equal to constant. Next, T will be equal to, this will be T into, now specific volume. Here this can be solved by using the law of indices, that is a raised to m into a raised to n is equal to a raised to m plus n. So here I can write this as v raised to gamma into v raised to minus gamma, that is equal to v raised to gamma minus 1. So in place of this I can write down v raised to gamma minus 1 is equal to, now C upon R, I'll shift R here, so that will give rise to another constant which I'll say that it is C dash, and this C dash is equal to C upon R. So from this I get the first relation, and here I'll keep this as equation number 3. Third equation. Next I'll again use this law, that is I can say that also PV raised to gamma is equal to constant. And now previously what I have done is put the value of pressure. Next in this case I am going to put the value of volume, which is specific volume, RT upon P, that I am going to put here. So therefore P into RT upon P raised to gamma is equal to constant. Next here P will remain as it is. Then even R, if I send it onto the right hand side, that will be C upon R, giving rise to another constant, and here this will be P T raised to gamma. Next here I am having P which will be raised to gamma, it is in the denominator, so this will be P raised to gamma is equal to C upon R. Next, after reaching at this stage, so therefore if I bring this P into the denominator, so that will give me, first of all, T raised to gamma will remain as it is. Next here it is raised to power 1. So if I send this P into the denominator, it will become P raised to gamma will be as it is into here P raised to minus 1 is equal to C upon R, which is another constant C dash. So from this I'll get it T raised to gamma is equal to therefore T raised to gamma is equal to P upon gamma minus 1 is equal to C dash. Therefore I can put T in the numerator, shift gamma into the denominator, so that will be P raised to gamma minus 1 upon this gamma, and this is equal to C dash, and here I'll call this as equation number 4. Next, after reaching at this stage, here I can say that now I am applying the governing law for adiabatic process at state 1 and state 2. So I can say that since P1 V1 raised to gamma is equal to P2 V2 raised to gamma, that is equal to constant. Next, therefore I will write down P2 upon P1, P1 will be shifted, that will be equal to V1 upon V2, and that complete is raised to gamma because both of them are having raised to power gamma. So if I write V1 raised to gamma upon V2 raised to gamma, I can write them as V1 by V2 raised to the power gamma as a complete equation. Next, after reaching at this stage, I can say that I have got the relation between pressure and volume. So keeping this as equation 5th, next I can say that I will be using equation number 3. Now after reaching at equation number 5, I'll be using equation 3, that is from equation number 3. We are having T into V raised to gamma minus 1. Now this I can write for state 1, so it will be T1 into V1 raised to gamma minus 1 is equal to, now it is constant, so I can write it for state 2 as well, so that will be equal to T2 into V2 raised to gamma minus 1. So therefore T2 upon T1 will be equal to V1 raised to gamma minus 1 upon V2 raised to gamma minus 1. So from this, T2 by T1 is equal to V1 by V2 common raised to the power gamma minus 1. So I'll keep this as equation A. Next, after this I'll be using equation number 4, that is from equation 4 I'll say that here I had written T upon P raised to gamma minus 1 upon gamma, so I can, it is constant, so I can write it for state 1 and state 2, so that will become T1 upon P1 raised to gamma minus 1 upon gamma is equal to T2 upon P2 raised to gamma minus 1 upon gamma. So therefore T2, I'll shift T1 on one side, so T2 upon T1 is equal to P2 raised to gamma minus 1 upon gamma upon P1 raised to gamma minus 1 upon gamma. So therefore T2 upon T1 is equal to P2 by P1 can be written like this, numerator upon denominator, and common raised to the power gamma minus 1 upon gamma. So this I'll keep it as equation number B. Now I'll be combining equations A and B to give the relation between temperature, volume and pressure for adiabatic process. So I'll say that therefore combining equations A and B, we get T2 upon T1 is equal to P2 upon P1 raised to gamma minus 1 upon gamma is equal to V1 upon V2 raised to gamma minus 1. So here I'll be keeping this equation as equation 1. So therefore from equation number 1 we get the relation between pressure, volume and temperature for reversible adiabatic or isentropic, because that is the other name of reversible adiabatic process, isentropic process. So here we have derived the relation between temperature, pressure and volume for adiabatic process. The next step would be to find the equation of work done for reversible adiabatic process. Now after reaching at this stage, I'll say that work done in reversible adiabatic also called as isentropic process. It is given by, now the relation of work done, we know that it is given by integral P into dV. That is the general equation of work done, because this integration of pressure into change in volume, that is area under the PV diagram, gives us the amount of work done. So this is the general formula. Next, it is applied over volume V1 to V2. Now since I can use the equation, that first I will be keeping this work done equation as first equation number small 1. Now I will say that since PV raised to gamma is equal to constant, that is for isentropic process, that is reversible adiabatic process, this is the governing law. So therefore pressure P will be equal to C upon V raised to gamma. Next I will be putting this value of P in equation number 1. So therefore put the value of P in equation small 1. So therefore we have work done is equal to integration of P, which is C upon V raised to gamma, with respect to dV. Now after reaching at this stage, here I can take C, since it is constant, so it is outside the integration sign. Here I have 1 upon V raised to gamma, which can be written as V raised to minus gamma into dV, integrating between V1 to V2. So finally I will get work done as, therefore work done is equal to C into V raised to minus gamma, the integration is V raised to minus gamma plus 1 upon minus gamma plus 1, integrating from V1 to V2, that is the lower and higher limits respectively. So therefore work done will be equal to C into this V, instead of this I can write down V2 raised to minus gamma plus 1 minus V1 raised to minus gamma plus 1 divided by minus gamma plus 1. Next, after reaching at this step, I can say that if I want to change the sign throughout, then if I take negative common, so there will be, therefore work done is equal to, that is changing the sign of the numerator and denominator simultaneously. So here I will be having, instead of V2, first there will be V1 raised to minus gamma plus 1, and here minus V2, that is I have changed the sign of the numerator. So similarly the sign of the denominator will also change, and that will be gamma minus 1, because if I take negative common from the denominator, it will become gamma minus 1, and from the numerator negative is taken common. So negative gets cancelled out, and I reach a step here. Now after reaching at this stage, we know that this constant is nothing but P1 V1 raised to gamma is equal to P2 V2 raised to gamma. That is the governing law for adiabatic process. So therefore I can write down the work done in the form of, now C, if I multiply it with V1, it will become P1 V1 raised to gamma, that is the value of C, into V1 raised to minus gamma plus 1, then minus, instead of C, next if it is multiplying with V2, so P2 V2 raised to gamma into V2 raised to minus gamma plus 1 upon gamma minus 1, and I have used this relation since P1 V1 raised to gamma is equal to P2 V2 raised to gamma, which is a constant value. Now when I simplify this, V1 raised to gamma into V1 raised to minus gamma plus 1, that will be, here gamma then this will be minus gamma plus 1. So plus gamma minus gamma will get cancelled out. We have V1. Similarly for V2, this will be gamma minus gamma, both of them will cancel out, and this will be only V2. So the final formula of work done will be, therefore work done will be equal to P1 V1 minus P2 V2 upon gamma minus 1. Next, we can say that also PV is equal to MRT, that is the characteristic gas equation. So therefore work done, instead of P1 V1 I can write down it is MRT1, P2 V2 I can write down MRT2 divided by gamma minus 1. So therefore work done will become M into R T1 minus T2 upon gamma minus 1. So I'll call this as equation capital 1. Here this is capital 2. So I can say that from equation 1 and 2, work done for reversible adiabatic process can be found out. So this is the formula of work done in case of reversible adiabatic or isentropic process. Now after completing the work done, we are going to see the change in internal energy, and as we know, in case of reversible adiabatic process the heat transfer is 0. Now I can say that heat transfer during adiabatic process, which is a reversible adiabatic process, is given by, heat transfer is given by the general equation, that is equal to work done plus change in internal energy. This is by first law of thermodynamics. Now I can say that since heat transfer Q is equal to 0 for reversible adiabatic process, so if Q is equal to 0, therefore work done plus change in internal energy is equal to 0, and work done will be equal to minus of change in internal energy. It means if the internal energy decreases, then the work done increases. So that is a case of expansion, that is when the gases are expanding, the internal energy of the system, it decreases, but the work done on the piston, external work which is provided by the gases, that work done increases. So there is increase in work done with decrease in internal energy. And if I say the opposite, that is if we are providing work input, that will increase. If we are working on the system, then work done will become negative, and in that case internal energy or change in internal energy will be positive. So the amount of work done goes into increasing the internal energy. So here from this I can say that I'll call this as equation 1. So here there is a conclusion for this, that is from equation number 1 it can be explained that, here I'll write 2 points. First, when change in internal energy decreases, then the work done by the system increases, which means expansion process. So if the change in internal energy decreases, that will result in positive work, and which is called as the expansion process. Next, when change in internal energy increases because of work done on the system. If the work is done on the system, it means that is a negative work. If the work is done by the system, that is positive work. So positive work is achieved when the change in internal energy decreases. Negative work when we are doing work on the system, then the internal energy increases. So because of work done on the system, which means compression process. So here we can understand that in case of expansion, the piston would be moving up. That is, I'll explain it with the help of a diagram which we have previously seen in case of the reversible adiabatic process. From this diagram, I can explain that when the internal energy of the gases are decreasing, internal energy of the gases will decrease when there is expansion. So forces will be exerted on the piston and we are going to get the positive work from the system, which is called as expansion. If the case is reversed, that is, if we are doing work on the gases, applying the work from outside, so this is the negative work because work is done on the system. If work is done by the system, that is positive work, and if it is done on the system, so negative work. So if the work done is negative onto the gases, that will result in increase in internal energy, and that indicates compression process. So in this video we have seen the reversible adiabatic process, also called as isentropic process, in detail.